Okay, thank you. So thank you for the introduction. And so today's topic is the Euler and Kohlberg system machinery. And you will see many overlaps with the Francesca's lecture. But there is also difference because I will mainly concern the cyclotomic extension of Q, not ring class extension of the imaginary quadratic field. So let me recall the theme. Is we want to understand the size or structure of the arithmetically interesting groups, including, for example, class groups of number fields or Selma groups we mainly deal with in this lecture series. And of course, is quotient T-Shafarish group, mainly P part, after fixing a P. And we want to make the connection, this guy, with the values of the corresponding L functions. And the role of the Euler system in this theme, or like an advantage, is if we have the non-zero Euler systems, then we can bound the Selma groups from above. So the role of Euler systems is, so if I have a non-zero Euler system in the bottom class, so in my case, ZQ, and Higino point case over the imaginary quadratic field, and if I have a non-zero such thing, then so people usually say by Euler system machinery, we get an upper bound of Selma groups. And yeah, this is so-called Euler system machinery. And due to, of course, Rubin, Kato, and Peong-Ryu, and this machinery itself is today's focus. And plus some argument in the Kohlberg systems. So when I say Euler systems, it has two properties. How can I say that? And a bunch of comerge classes, like a Q, sorry, it's a MPN, lies in H1, is a abelian extension, and the certain periodic representation. And what do we expect from the word Euler system is the first norm compatibility, of course. And the other is they're making the connection with the L value. For example, the connection with L values. For example, if I have the bottom class, then we hope this guy is connected with the L value of the dual representation at the central critical point. Okay, this is the what we expect, and we start with a bit more general setup. And I fix a prime larger than 2, and F is a finite extension of QP. And its ring of integers O, math scale O, and the maximal ideal MF is generated by uniformizer Vapai. And T is a free O module of finite rank N, and with continuous linear action of the absolute Galois group of Q. And we say T is geometric. Geometry means like if you are not like familiar with this kind of thing, is you can regard it as reasonably good. If T is unramified outside the finite set of primes, usually denoted by sigma. And at P, we hope this guy is a drum at P in the sense of Fontaine. So these are like what we are interested in. And that then the Galois representation following this linear action factors through the maximal extension of Q unramified outside sigma indeed. So the corresponding Galois representation in fact factors through, I just notified this is Galois group of Q sigma over Q maps to the O linear automorphism of T, which is isomorphic to ZL and O. Of course, if you don't like the consider general things, this T is just the Tate module of the elliptic curve. And V is the drum means yes, you're right. And considering the coefficient also. V is T tensor F, and W is the divisible, I mean discrete Galois module, is V quotient by T. And if you are not familiar with this kind of discrete module, then this is just to consider P power torsion points. And for each M, integer M, larger than or equal to 0, then we say Wm is this M torsion. So how can I say this? It's bar pi minus M times T over T, which is just the W bar pi M torsion. And this is isomorphic to also like a T quotient by bar pi MT. Base field, which base field? Base field of the coefficient or base field of the Galois group? Base field of Galois group is of course Q, as I said here, and my coefficient field is finite extension of QP. So the coefficient field is periodic. Yeah. Okay. Now I consider it's dual. So star means the linear dual, and 1 is the taking Tate twist, which means so Hom O linear map so T2 O1, and you can expect the V star 1 is also defined in the same manner. And W star 1 is the quotient of V star 1.
There are
Sorry?
2 questions.
Sorry?
There are 2 questions in the chat box.
Yes, I think I answered during the lecture.
Okay. Okay.
Yeah. Okay, W star 1 is V star 1 quotient by T star 1. That's how I define in the dual side. Then the corresponding L functions and Selma groups can be defined as follows. And Selma groups. So for a so-called a good prime, which means like a not in sigma, then its Euler factor is defined, a version of the Euler factor is defined as follows. So Tx is, so T is the Gauss representation, X is the variable. So determinant is it of In, because it's n-dimensional rank n representation, and X times rho Frobenius set L acting on T. And here I choose arithmetic Frobenius for convenience. And set the sigma imprimitive L function is product of all primes not in sigma, and PT putting the L to the minus S and taking the inverse. And we expect this guy converges for S, whose the real part is very large. This is how we define the L functions. And for the bad prime, we can also define the factors in good cases and local condition for Selma groups. And okay, so for finite condition, for V is the kernel of H1 QLV to H1 the inertia group part. So this is a restriction map, and this guy is inertia at L, inertia subgroup at L. For all prime L, which is not Pn infinity, then for the T and W, we can just take the preimage and image. So what I mean is that QLT and H1F QLW are defined by using the map. Are defined as preimage and image of this guy with respect to the natural map T maps to V maps to W, respectively. Okay. And since we consider P is odd, so infinity prime, we do not have to worry about that. We will just put 0. Whatever Gauss module appear here, and yeah, we just put 0. And L equals P, then we have 2 things. First, we can just take 0 for p-strict Selma groups. So we denote by like a cell P or cell 0. I think we will use both notation. Sorry about that. And another condition, so-called the Bloch-Kato local condition. And you don't have to worry about that if you want to only consider the elliptic curve. You can just use the usual thing, and they are same. But in general, you can just define like this: the kernel of H1 QPV goes to H1 QPV tensor, so-called crystalline period ring. That's how we define the Bloch-Kato local condition. How we define the local conditions for like a general periodic representation. Okay. And we write the singular part in Francesca's talk. I use the quotient by F. Whatever it is, this means this. So in Francesca's lecture, H1 singular. Then we define the Selma group as follows, the various Selma groups as follows. So let me choose a sigma prime, another finite set of primes. And it's okay to assume this. The original sigma and sigma prime are like there is no intersection. Then we define the sigma prime relaxed Selma groups. Sorry about the difference of notation with Francesca. For W, for example, is the kernel global Galois cohomology. Just here, and this means in this case, like I consider this guy as Gal Q sigma union sigma prime over Q. That's how I think of this global Galois cohomology. Goes to the prime is L contained. Sorry, it's not in sigma prime. QLW. So there is no like a condition in the sigma prime. So it gets larger than usual Selma groups. So this is sigma prime relaxed Selma. And certainly this guy contains the usual Selma group. Kernel H1 QW. And here we can just, so one thing I forgot to say is when we define the just Selma groups, the choice of sigma is, so the definition is independent of the choice of sigma. So here in my mind, I just consider this Galois group. And let me see, so, okay. Like this, H1 F QLW, like this. And okay. And also in the opposite case, we also consider sigma prime strict Selma groups. Here's the kernel. Let me just put the relaxed Selma, but like we put the strict local condition here. Something like that. So this is the usual Selma. And this guy is the sigma prime strict Selmer. That's the one goal, the objects we deal with. And in this situation, was a weak form of the Bloch-Kato conjecture is as follows. The vanishing order of the L function something like that is, VT doesn't matter in this. It's same as the dimension of this Selmer group, but it's dual minus the dimension of the invariant of the dual representation. That's the weak form of the weak form of the Bloch-Kato conjecture. Okay, with this notion, we can define the notion of the Euler system. Definition. This Euler system. And okay, rho and t's are as before. So we have the periodical representation, and for convenience, we fix the maximal abelian extension and another sufficiently large extension K, mathematical K, and this guy contains the like large number of, I mean, it's very big. Means as follows. So K contains, that's a capital. So okay, so cyclotomic zip extension and maximal P extension of the Q as joining zeta Q. Q is a different prime. So Q, I will explain this notation immediately. For almost all prime Q congruent 1 modulo P, where so Q zeta, so Q is a prime, and like this, and maximal P sub extension of this cyclotomic extension. Maximal P sub extension. And but you can just work with this guy. Yeah. This difference does not change too much. So sometimes I work with this, sometimes I work with this. From Euler system, vanishing as, let's see. I mean, depending on the depending on the normalization, of course, is the if I consider like how can I say that? So let me just say central critical point. No, nothing more than that. Sorry about because I didn't fix any like a weight. Euler system for this T and the big extension K is a cohomology, the collection of cohomology classes. Say Z underline. ZK lies in H1 KT, and Q is contained in just K, and this normal K is contained in the mathematical K, and this is finite. So finite abelian extension. So satisfying the following the norm relation. So norm, in this case, norm is a co-restriction, of course. So to be explicit, let me just write down like this. So Q, zeta, and L, or you can just write down NL, but for the convenience, I will write down like this. So zeta NL, and this is zeta N, and zeta Q, zeta NL. So I just consider this guy contains all this guy. It doesn't matter. Is Z Q zeta N if L divides N, or L is contained in sigma. And otherwise, then it splits the Euler vector in the dual side. But the variable will change the inverse of Frobenius. So this shows that all this collection of congruent classes really remembers Euler vectors. So it seems reasonable to say that it is a Euler system. And a rough picture is, so if you have the Euler system of the sum of billion extension Q zeta N, and it corresponds to some sigma at an imprimitive L value. Sorry, it's it's some central critical point, or 0 or 1 following your normalization. And sigma N here is the sigma, and sigma and the all primes dividing N. In this situation, so theorem, how of Lubin shows the following. So let G on the line be an Euler system for this Tian big extension K, and assume two conditions. In his book, it is called like a hypothesis QV, which is the first condition is that there exists tau in the Galois group of Q bar over Q as joining all P power roots of unity, such that V quotient by rho tau minus 1 V is one-dimensional over F. So which requires the image is large. Also assume like a V is as a Galois representation is irreducible. Okay, in this situation, F ZQ in the bottom class in the T is not torsion, then it bounds not just Selma groups, but like a p-strict Selma groups. Of its dual. So it's finite. So in the case of elliptic curves, like using wave pairing is self-dual, so you don't have to worry about it too much. But in general, you need to care its duality stuff. And ideal proof is already, Francesca said much about that. Let me briefly sketch also. So what we want to do is that we want to bound this guy modulo P to the M, but independent of M. So bound cell P Q W star 1 independent. So sorry, it's M. So WM. Sorry, it's taking the dual of the WM. That's what I meant. Independent of M. And all the tools are same as before. So as in the Franciscan's lecture, is local and global dualities. So the local duality means here, so pairing L is first the local cohomology of WM times H1, and WM star 1 goes to H2 QL O quotient by the P to the M, something like that, and taking the Tate twist, which is isomorphic to just this Artinian ring. And yeah, this shows H1. So local duality says like a finite part is self-orthogonal. Orthogonal to each other. Sorry, I didn't identify them. So something like this. Okay, now we put sigma prime in certain primes, then the global duality says the following. So consider the diagram, which you already saw in Francisca's lecture, but I give a little bit different interpretation, but equivalent, of course. So in there will be two sequences, of course. So the first start with the P relaxed Selmer. And goes to P and sigma prime relaxed Selmer. Then the last will be the sum of L runs over sigma prime and H1, the singular part of the local cohomology. And this map, I will call it local S and sigma prime. On the dual side, goes to as follows. So here I put so making the correspondence, I will put here sigma prime and P strict Selmer. Don't forget the dual. And here, the P strict Selmer appears, which we want to really bound, and goes to local. So this map, I just write down like this. And okay. Then here, not singular, but finite part appears in dual. Okay, good. And another way to connect this is the taking the pairing these two goes to O, and this is sum of all the local pairings. It's completely equivalent to saying what Francesca did. And in this situation, global duality means so the image of this guy and image of this guy are orthogonal to each other. And image Okay. Then taking orthogonal. Orthogonal with respect to this pairing. So what we want to do is that we want to bound this. So I hope this guy gets smaller. In order to do that, we should make this image get larger. So yeah. So what we want to do is that finding many derivative classes in here to make this guy larger and larger. That's the how the intuition works. So the idea is the let me write it in the next page. Construct sigma naught. So it will be the bunch of the Kolyvagin primes, but in my sense, in the cyclotomic setting, the cyclotomic setting, the definition of the Kolyvagin primes are different from the anti-cyclotomic one. And the corresponding kappa sigma prime lies in Selmer p relaxed and sigma prime relaxed to Wn. That's the Kolyvagin derivative classes. From Z, such that the size of cokernel, then local S, and the size of sigma prime and P strict Selmer they're bounded independently of M. That's the how the idea works, and yeah, this part is a bit more non-trivial. It's because we consider all the p power congruence. So in this situation, so this sigma prime will be another like a Kolyvagin primes, but for cyclotomic setting. So L is a Kolyvagin prime in the for Kato-Joyle system is a bit different. So L is still need to be good prime first, and L is not congruent to -1. L is congruent 1 modulo p to the m. So because we work over all the higher power congruence, and AL is congruent to L plus 1 modulo p to the m. That's our convention of the Kolyvagin primes. And still, yes, using Chebotarev density theorem, there are lots of Kolyvagin primes. Of course, we make the power higher and higher, the density gets lower and lower. So that's the one bad thing if you really work with the practically, but there are infinitely many still. So remark is there are infinitely many Kolyvagin primes due to Chebotarev density theorem. So as a consequence, we have the finiteness of the p-strict Selma groups. So one difference from the Higgins point setting is that in the Higgins point setting, we directly get the finiteness of the Selma groups of elliptic curves over imaginary quadratic field. Density m tends to infinity. Of course, as it gets, yeah, it's very small, but in its finite layer, of course, there are still like positive density. So in its finite layer, we don't have to worry about that. So how can I say that? So when we deal with like a Kolyvagin system arguments, we do not work with the characteristic zero situation. We only consider something modulo p to the power. So we get the finiteness of this. That's the kind of story. And so which make us a bit unhappy because what we want to bound is a Selma group, not p-strict Selma groups. So we want to upgrade. So upgrade to the finiteness of just the usual Selma group. Then in order to do that, we now focus on the case of the curves. Now we really need such a setting. So move to restrict ourselves to the case of elliptic curves. To the case of elliptic curves. Okay. Then what we want to do is the following. So we want to measure the difference. So difference between, now we are on the elliptic curve. So I mean, if I write down like this means cell 0, so p-strict Selma e to infinity, and just cell qw star 1 is just Selma group of elliptic curve. And using the same diagram in the global duality, but with a Bloch-Kato local condition at P. Yeah. Same diagram works with a Bloch-Kato local condition at P. Which means as follows. So, okay, now the Galois module will be a bit different. So 0 goes to Selma group of the Tate module, and P relaxed Selma group with a Tate module goes to H1 singular in P, T here. So this map is localization map. And on the other side, cell 0, Q, EP infinity goes to cell, yeah, just the usual Selma group. And the localization map goes to the local condition at P, and this goes to QP mod ZP with the usual global duality, with image of the this first localization map is also going to image of the second localization map. Okay, so we have this now. So now, in order to have the finiteness of this guy, what we need to show is this map is surjective. So in order to show cell QE P infinity is finite, then enough to show the following. So to look now, I will invert P in the first line. So localization map from the P relaxed Selmer to V is I inverted P here, local P and H1 QPV and H1 singular part S, and this maps to via dual exponential map. Is the kernel of dual exponential map is a finite part, so this is isomorphism, and it goes to the field zero of decrease of V. If you don't want this horrible notation, this is nothing but the QP times invariant differential. And the explicit reciprocity law shows that the bottom class of Euler system maps to here, then you will get L value. The pith Euler factor is removed here. So if L value doesn't vanish, this guy is non-zero. So all these are isomorphism. So look, this map is surjective, which forces to the image of this guy is finite. So this is finite. So Selma is finite. That's how it works. Okay, and the last of time, I will move our interest to the Kolyvagin system, not just the Euler system. Okay. Move to Kolyvagin system. Give me a second. Okay, first, why? So I said once there are two advantages. First, we may not just have, but we may be able to detect to have the equality. So sharp bound can be detected via so-called primitivity of Kolyvagin system. This is a multi criterion. Another thing is the structure theorem. So not only size. So, so Francesco also mentioned like Coulibagin's 1991 work. So, and his conjecture. His work on the or how can I say that? Sorry, it's the let me just say like a Coulibagin's conjecture on the non-vanishing of the let me say the Huguenot point Coulibagan system. Its motivation is the we can like from if we know this conjecture, then we can like we can determine the structure of Selma groups. In terms of this Huguenot point Coulibagan system structure of, so in this case, in this like Huguenot point case, cell K EP infinity in terms of Huguenot point Coulibagan system. So this structure theorem is the kind of motivation of this Coulibagan conjecture. And we can do similar thing in the cycloatomic Euler system, for example, Kato zero system here. So here's the one like then the dramatical change. So I have the Euler system, and let me assume my bottom class is non-zero. And what we've seen up to now is that it implies the Selma group, P-strict Selma group is finite. Right? That's the work. I mean, this is the main result of Coulibagan. Main result of the Euler system argument. But if we change all the idea to the Coulibagan system, then okay, first as we've seen in the Francesco's lectures, we construct the Coulibagan system. I usually write down like kappa n is the square-free product of Coulibagan primes in its setting. And this is in fact equivalent to the very first class in the Coulibagan system is non-zero, indeed they are same. But in this situation, you have more information. We can determine the structure of the P-strict Selma group in terms of kappa n. So this is a kind of upgrade. Of course, this upgrade is not free. So what should we do? What's the cost? And as we've seen, if we take the usual like Coulibagan derivative process, so I chose like sigma prime, which is square-free product of of the Coulibagan primes. Okay, so it's the a finite set of Coulibagan primes we've chosen. Then let me just say n is product of square-free product of L in here, okay, for convenience. So then this n will be this n indeed. Then the derived class kappa n And by nature, we know the cell P relaxed and the sigma prime relaxed and QWM. That's the only thing we know now. And what Major and Rubin did is they gave a more control of the local condition of these classes by adapting a complicated formula, but the formula is not required for our case. That's the one good thing. So how can I say that? So Major and Rubin organized this kappa n with more controlled local conditions at sigma prime. That's what the Major Rubin said, get more rigidity of their classes in their book. And this more controlled local conditions allows us to have the structure theorem. Okay, now let me introduce what they are. Is the F L is congruent to 1 modulo P to the M, then so-called the transverse local condition is defined as follows. So H1 transverse QLWM is the kernel from the usual local cohomology to the slight restriction map to H1 QL, but adjoining zeta L and WM. This is called the transverse local condition at L. And in fact, this plays the role of the kind of complement of the finite local condition. The finite local condition. Another way to say this is so making the singular part as a submodule, not just quotient module. And also, there exists so-called finite singular comparison map. So from the H1F, QL and WM, and goes to a certain map, the phi L finite singular Fs, and it goes to H1 singular part QL WM, which is isomorphic to H1 transverse QL WM. And this map is indeed obtained from the Euler factors at L, but I will not give the detail here. So obtained from the Euler factor at L. And okay, what we want to hope is the construct of the following classes. So we want our kappa n lies in P relaxed, but N transverse, which means like i.e. if L divides N, then if I take the localization at L, then it lies in the transverse part. And so in general, there is a complicated formula to construct the Kolyvagin systems from the Kolyvagin derivative classes, but it turns out that in Kato-Zora system, we do not need such a process. That's the one very good thing. So indeed, and what's the axiom of the Kolyvagin system is the following. So this is implicitly already given in Francesco's talk. What he did in the very last moment of the lecture is related to following equality. So the axiom of Kolyvagin system. So all the kappa n's, the collection of kappa n's are called the Kolyvagin system, and satisfying this relation. So localization of kappa n L is related to localization at L of kappa n, but they lies in the different space. So I take the finite singular comparison map. So this is the axiom. So a bunch of kappa n satisfying this relation is called the Kolyvagin system. And proposition is, so H1F, the finite local conditions are orthogonal complement to each other via local type pairing, right? This is the limit orthogonal complement to each other via local type pairing. I guess so. Yes. Yeah. Thank you. Yeah. All right. Okay. And one good thing is that the transverse local condition satisfy the same thing, same the orthogonal complement property. That's one good thing. Let me just write ditto. And one remark is there are like lots of developments in the theory of Kolyvagin system, but we in this lecture series I only consider the most classical one. So yes, we only consider so-called core rank 1 case. And of course, there is a higher core rank Kolyvagin system, which are very important nowadays, with many applications, and another is so-called star systems. And there are many developments are done, and we still need the image of Gauss representation is large. Representation is large. This is required to satisfy all the conditions to have the Kolyvagin system. And P is, yes, in the original Kolyvagin system argument, 3 is excluded if the representation is self-dual. So the elliptic curve satisfies this condition in major Rubin. But like a p equal 3 case is recently this condition is removed by Sakamoto recently. So for other prime, it's okay. Okay, now we derive the Kato's Kohlbergian systems from the Kato-Zora system. And all the process is very similar to the Higino point case. So, okay, so do this. So G bar is ZK, K is Kato's Euler system for elliptic curve E. And so I want to more specify the choice. So choice can be characterized as follows. So H1 KT is characterized by its interpolation formula. So sigma runs over Galois group of K over Q, and sigma acting on the dual exponential localization, and ZK times chi sigma. So chi is of course, the character of this Galois group is is the SP imprimitive L value, and chi1 divided by the positive period omega E is an invariant differential where chi is an even character of Galois group of K over Q, and odd character, all the values are 0. So I will only consider cyclotomic ZP extension. And S is the product of all ramified primes in K over Q. Ramified primes. K over Q. And let me recall the notion of Kohlbergian primes again. And PM is the set of prime L satisfying L is a good prime and not P. And AL is congruent to L plus 1 modulo P to the M. And L is congruent to 1 modulo P to the M. And each prime L, we also fix a primitive root modulo L. Primitive root eta L, and fix an isomorphism. So Galois group of Q adjoining zeta L over Q is isomorphic to Z mod LZ cross. And eta L, we denote, so it's generated as sigma eta L. Note that its order is the L minus 1, but so in the Kohlbergian derivative operator is defined as similarly, but like its order is different now. I runs over 1 to L minus 2, I times sigma eta I and zeta L to the I. That's the and for square-free product of L, named N, is the product of DL. Let's see. And the construction is very similar, even simpler. So I start from ZQ as joining zeta n is the H1 Q zeta n T, and take the derivative dn ZQ zeta n in the same cohomologous group, and take the mod Pn reduction, mod Pm reduction. Then first, let me write down like this. So dn and mod P to the m H1 Q zeta n T quotient by Pm. And as we've seen in Francesca's lecture, this is indeed lies in the Galois invariant of this quotient. So H1 Q zeta n T quotient by P to the m and invariant by Gn. Gn is Galois group of Q zeta n over Q. So this guy lies in here. So dn ZQ zeta n modulo P to the m. Yes. Oh, sorry, L function generally satisfies functional equation. Can I mean, yeah, that's a very good question indeed. So one funny thing is that in Kato's Kolyvagin system controls P-strict Selma groups, which has no functional equation at all, right? So Kato's Kolyvagin systems themselves does not have any functional equation as far as I know, but I think at the end of the lecture, I will say this or not, but like, so-called I named it Kurihara number, so-called delta n, it satisfies certain functional equation, which can be regarded as the modular symbol version of Kolyvagin system, Kato's Kolyvagin system. And okay, and this guy maps to, now the quotient go into in the cohomologous group, H1 Q zeta n T modulo P to the m T and Gn, and the inverse of the restriction map gives us the Q, here, and the final image is the kappa n. Yes, that's how we get this. And as I said, this so in the cyclotomic unit case, for example, there is like a formula to modifying this to get real Kolyvagin systems. So a priori, this guy, we don't know is the local condition of this, but basically the remark is in general, there exists a complicated formula. How much complicated? So if you look at the Major Rubin's book, these formulas in the appendix for kappa n from just the Kolyvagin derivative classes. But we do not need it for the Kato's Kolyvagin system, and also Higgins-point Kolyvagin system, we don't need it indeed. We do not need the formula. So in principle, the reason is the Euler system is how can I say that? Sorry, Euler factors are quadratic. That's the reason. Yeah. Are these Kolyvagin derivatives related to any way to derivative of L function? Yeah, that's a good question, and I would say that these Kolyvagin derivatives would define a new version of derivative of L value. That's how I understand this Kolyvagin derivative. Okay, now I present some idea of the Kolyvagin system argument, not just the Euler system argument. In what I want to say is that how do we get a structure theorem? So the idea of Kolyvagin system argument, which means a structure theorem. How can you get the structure theorem? So, okay, notation. So kappa underline is the all Kolyvagin systems, and n is the Kolyvagin system modulo p, but like it contains all higher power congruents also. So, and this is the scale-free product of Kolyvagin primes. P1. And yeah, for each n in M, so scale-free product of the Kolyvagin primes modulo p to the m, the lambda n EPM is defined to be length of the ring is the, of course, G mod PMZ is the, okay, now I just put 0 for P strict and transverse sum group. And partial R and kappa is the minimal number from M minus length of the module generated by kappa n, sorry, it's the G modulo P to the MZ times generated by a certain Kolyvagin system class kappa n. And yes, kappa n, and I put, sorry about the complicated notation, but I think I need it. M here, and okay, I need to make a connection with this n and this r. N is of course the lies in here, but the number of divisor of n is r. Where, okay, this upper m, what's the meaning of upper m is the where kappa m is kappa modulo p to the m. Okay. And EI, so yeah, I can just all modulo p to the m, then I have this is the partial I kappa m minus partial I plus 1 and kappa m m. And so yeah, maybe I can just m here also. Yeah, sorry. And I is larger than or equal to 0, and this guy will be the elementary divisors of the p-strict Salma groups. Okay, and the theorem is as follows. So kappa n m is first is non-zero for some n. And this is the assumption. So this is the kind of the version of the Kolyvagin's conjecture for Kato's Kolyvagin system. But after having this, we have the following structure theorem for p-strict Salma group. So I runs so over 1, 2, and z modulo p to the diz with, so di's are decreasing, and this number, partial r, kappa m, is equal to minimum of m, or j plus sum of di, and I is bigger than r, where I need to specify j. J is larger than or equal to 0 and satisfies the following equality. So z mod, sorry about the complication, but that's how it works. Kappa n modulo p to the m is same as p to the j plus lambda n e p to the m times Selmer. Now p relaxed and n transverse Selmer group. And it is known that this j is independent of n. Okay, so yeah. So P-Selmer group is this, is isomorphic to this, and all di's can be determined by using all this, especially its the differences, right? Because of this. So this EI plays a role of the elementary divisor of this, I mean, for this abelian group, finite abelian group. That's the statement. And okay, let me briefly sketch the how, not really proof, but how it works. And n transverse is really important in this process. First, in this inclusion, so it is easy when so-called R is 0, and even we get equality here, then consider the following map. So cell P strict Q E P M goes to a bunch of localization map, EQL, tensor Z mod P to the MZ, which is the isomorphic to Z mod PMZ, and the number of the divisor of n, like this, the free module over the Z mod PMZ, and its kernel is contained in cell P strict and the n transverse sum group. In fact, it will be like a P strict and n strict also sum group. So it is obviously contained in here. And how about the other side? And using the Chebotarev density theorem, and we can choose a prime, choose a Kohlbergian prime L, with a slightly better property, such that, so because of this, like what we can say is because of the first, what we can do is that L strict Selmer which is the submodule of the original P strict Selmer group, really remove the largest factor in the decomposition. I starts from 2 Z mod P to the DIZ. So by adding the else strict local condition, we kill a generator. Also, in fact, in this case, this else strict condition is indeed L transverse local condition. So kill a generator. And then using the L transverse P strict Selma group, we repeat the process. So using induction. And we get a result in the structure P of the P strict Selma group. That's how it works. And yeah, let me stop here. Thank you.
Yeah, thank you very much, Chan Hokin. Are there any questions, comments? Okay, there doesn't seem to be any questions or comments. Thank you very much, Chan Hokin, for your lecture.